So thank you everyone for coming this early. So this is the first session today, Wavefronts and Aberrations. So our first speaker is Hassan, and he's an assistant professor of biomedical engineering and physics at Peking University, and he builds frontier imaging instruments that extend human vision for scientific discovery and advanced manufacturing. And his lab at Peking University combines physics-grounded algorithms, computational physics, control, and generative AI with hardware innovations for imaging at extreme scales. Yeah, we are happy to have him as an invited speaker, and let's welcome him.
Okay, so thanks for the nice introduction and good morning, everyone. It's a great pleasure to speak at ICCP. Today I'm going to talk about extreme adaptive optics, how we can control the light with extraordinary precision, first to imaging the Earth-like exoplanet, and then to think deeper in the biological tissues. I guess some of you may have already seen me in the adaptive optics summer class, but actually my own research on adaptive optics also started at Princeton when I was a junior PhD student in mechanical engineering. Back to 10 years ago, I was looking for an interesting control problem for my PhD thesis because I'm a big robotics fan and I want to work on control. And then that's the first time I heard about adaptive optics from my advisor, Professor Jeremy Casting. And Jeremy described it as a kind of black art that humans use to search for aliens beyond the solar system. And of course, in grant proposals, we call that direct imaging of exoplanets. Jeremy and I are both big fans of the science fiction three-body problem. I don't know how many of you have seen that. That story describes conflicts between our human and alien civilization in the neighboring star system called Proxima Centauri. So when Jeremy introduced that project to me, the scientific motivation was already quite exciting. Perhaps we can actually image the planets around our neighboring stars, hopefully without starting an interstellar war between humans and aliens. This is where the scientific fiction becomes unexpected, connected to reality. In 2016, exactly 10 years ago, astronomers actually discovered a planet in this same neighboring star system, Proxima Centauri, and the planet is called Proxima Centauri b. And although we haven't found the aliens, but we did find the planets. What is also remarkably is how recently this entire field emerged. Until early 1990s, actually, we have no idea or no confirmed evidence of planets orbiting around the sun like stars. But over the past 3 decades, astronomers have discovered thousands of exoplanets using several different methods, and this revolution was recognized by the 2019 Nobel Prize in Physics Award. However, despite this progress, most known exoplanets have never been directly imaged. They were mainly discovered using indirect method. For example, on the left side of the slice, with the transit method, we do not observe the planet itself. Instead, we measure a tiny periodical reduction in the brightness of the host stars when the planet passes in front of it. The reason is pretty simple because a planet does not usually emit much visible light by itself. It only reflects the light from their parent star. In that case, an Earth-like planet can be approximately 10 billion times fainter than the sun-like star. Therefore, if we want to directly image or collect photons from the planets, we need a telescope system capable of achieving extremely high imaging contrast. However, the optical diffraction phenomena bring unique challenges for us to achieve the high contrast. Due to the limited size of the aperture, a point source can never be achieved. So the intensity of the diffraction halos of the stars actually decays relatively slowly away from the center. Therefore, when we observe a star and its planets, the faint planetary signals will be fully covered by the diffraction halos of the parent star. So even if the telescope has enough spatial resolution, it's really hard for us to directly image the planets. And that is exactly what happens when we try to observe the Proxima Centauri B using the Hubble Space Telescope. In fact, Hubble has observed Proxima Centauri many times over the past 3 decades. Because the diffraction halos and also the speckles created by the wavefront aberrations, we've never been able to really image the Proxima Centauri B. In the past several years, astronomers proposed diverse technologies to solve this problem. The most widely adopted solution combines 2 technologies. A chronograph to suppress the deterministic diffraction patterns, and then extreme adaptive optics to remove the residual starlights caused by the aberrations. A chronograph, maybe you have never heard about that. This is some devices which was invented originally for sun observations. It is a device that uses a series of optical masks to change the shapes of the point spread function. For example, this is a type of chronograph called shape pupil. We know that the Fourier transform of Gaussian is still a Gaussian, right? So if we have that shape of shape pupil, we can actually redistribute the energy in the focal plane and create 2 dark hole or high contrast areas on 2 sides of the point spread function. However, this can only be achieved with a perfect system, but real systems are never ideal. Surface errors, misalignment, or thermal effect will distort the wavefront aberrations, and that will create aberrative wavefront. And then there will be leaked light into the dark holes, so we can never achieve the contrast we need. That's why we need wavefront control, or what we call adaptive optics. With the help of the deformed mirrors, we can correct the wavefronts and finally achieve pretty high contrast. And the device we typically use for wavefront control is the deformed mirror, which is just an array of the actuators with a reflective continuous surface above that. This is the basic system of how we achieved high contrast X-planet imaging. Over the past few years, actually this combination has been demonstrated from the ground-based telescopes to space-based telescopes. However, because of the limitation of the atmospheric turbulence on ground-based telescopes, we can only achieve 10 to minus 6 or 10 to minus 7 contrast. So to really image Earth-like planets, we have to rely on space missions. The mission Jeremy suggests me to work on 10 years ago is the Roman Space Telescope, which is scheduled for launching next month, actually. And that will be the first space telescope with some chronograph and active wavefront control. And actually, in China, we're also planning a similar mission called China Space Station Telescope, which will also be implemented with a chronograph and wavefront control for the high contrast X-planet imaging. However, the control system or adaptive optics system used for ground-based telescope can be very different from those we want to use for the space missions. Conventional astronomical adaptive optics system primarily focus on, as I mentioned, the atmospheric phase correction. In that case, we split the light using beam splitters, and then we have a dedicated wavefront sensor for measuring the phase errors, and then a deformed mirror to inject approximately opposite shapes to compensate. This system runs at kilohertz, but the required precision is typically only tens to hundreds nanometers. But space-based extreme adaptive optics system is in a very different region. The aberrations evolves more slowly, but the required precision is below 1 nanometer or even sub-nanometer. At this precision, a conventional wavefront sensor suffers from non-common path errors. So we have to use the science camera to directly estimate the wavefront and then add the compositions on different mirrors. And also, since in the low R mass region, our aberrations becomes very high order wavefront aberrations. So we have to control with a higher degree of freedom. And also, since we are having a chronograph, that means in our system, we have to distinguish the PSF shapes caused by the diffraction element and those caused by wavefront aberrations. So we have to operate the AO jointly with DOE, and that's an even harder problem. A natural starting point is to use phase diversity, which we usually use in computational imaging to solve that problem. Basically here, we just add the perturbations on the default mirror, and this perturbation is known, and that will cause intensity changes on the image plane. And that will give us a chance to estimate the wavefront, and then we add controllers to compensate these aberrations. And then another loop, we can add more perturbations, another round of changes, and we do estimation. And this go again and again, and we can finally correct the wavefront aberrations in our system that reduce the contrast. However, this pipeline sounds reasonable, but there are also some limitations. First, typically in computational imaging, we just assume phase errors, and that will restrict our controls to specific conjugate planes. And then we don't like phase ratio because it is a non-convex optimization. So it can be slow and inaccurate. And also, with this assumption, we usually correct phase only, not amplitude aberrations. But because there are several free space propagations, even phase aberrations can be converted to amplitude. So that's something we have to solve for the high contrast imaging. So as a graduate student, measuring control, actually I spent a large part of my PhD investigating the optimal control theory of the extreme adaptive optics. After several years, I think we finally converged on a standard, partially observed closed loop control framework. And this reformulation significantly improved the performance of the system. And I think the key was the state space representation. So here we no longer assume that we have some specific model of the optical system. Instead, we just model the state space on the focal plane. Our state is just the complex electric field at the camera plane. And then we assume we have a very typical linear model we used for all the control system. And our input, some things we use for adjust the electric field is a different mirror command, and then we use a linear Jacobian system to map the relationship between the control command and the electric field. And that will help us to build very standard linear estimators and the linear controllers. Let me be more specific. Here, since our DM response can be linear in some regions, so we can do a very naive Taylor expansions to move the phase perturbations from the exponential terms to some linear terms. And that is true to some extent. I will tell you how we solve the nonlinear problems later. And this linear approximation actually help us to significantly improve the efficiency and accuracy of estimation. Because with those linear model, now we can build a linear estimators. What we do is that we just apply the pairwise probes, same positive and negative probes to our DM command. In that case, if we do a subtraction of the positive and negative intensity, and then we can create a linear projection of this complex wave field to some specific direction. So in this case, we can just build a linear estimator to regress the electric field. And notably, this is pretty good because this linear regression can happen on each single pixel, right? So because our state is on the focal plane, and there are no crosstalk between the electric field at different locations. So in that case, we can do everything in parallel pretty quickly. And also with the linear model, we can also use the information theory to calculate the lower bound of our estimation. So we can also design the optimal probes, exactly the optimal amplitude and optimal shapes, so that we can achieve pretty fast wavefront estimation. And once the field estimated, control become more directed, so we can define the objective at the linear energy inside dark hole and solve for the deformable mirrors compound that minimize the energy. So in that case, we didn't distinguish the diffractions caused by the DOE and the aberration. We just tell the controller what the ultimate goal we want to achieve. And we want to dig dark holes in this area, then let's do it. That directly solve the optimal control problem, and we can achieve a pretty good control result. That actually finally gave us the optimal control series for the focal plane extreme AO, and that can help us enable sub-nanometer control accuracy. That's a testbed we created at Princeton. So as you can see, we can easily achieve a pretty high contrast using the linear control with only 10 control loops, which means that only 30 to 40 images, which is even smaller or fewer than a single phase retrieval requirement. And also combined with the hyperspectral imagers, we can do the broadband wavefront sensing and control. You can see the prism bars on the right-hand side. So that's broadband control. However, as you may already realized, in our simulation, actually, sometimes we cannot achieve the optimal goal. It's because that we do a linear approximation, right? But that's not a big problem. We can add some machine learning part that we do a real-time adaptive control that can update our models iteration by iterations. So in that case, we can, I will show this result first. So at the beginning, probably the model is not accurate, but if we upgrade our models in every 10 iterations, then we can achieve pretty decent control speed, like achieve the optimal results. And more recently, we have been developed related wavefront sensor technologies for the China Space Station telescope for CST, and that's a similar 2-meter telescopes as Roman, where there are also chronograph instrument implemented. And we not only tested that in a constant or static aberrations, we still add some perturbations. As you can see in the first 200 iterations, we just let it go with static perturbation. But after 200 iterations, we just add some perturbations. And our closed loop control can maintain the contrast with high precision with disturbance. And if we don't have the control, it increases the contrast. But once we bring the control loops back, and it's soon degraded to the contrast we wanted them to happen. Okay, maybe last minute, I want to talk. So time really flies. So 4 years ago, I moved back to Peking University, and our department head asked me to build my own lab where we want to apply AO to microscope. At that time, I have no ideas about what a microscope could be. But he told me that the tissues is just like atmosphere for a telescope. So we just apply the same techniques to super resolution microscopy. What we do is pretty similar. So we just assume that the point source in the single molecule localization microscope are the stars. And we apply same techniques to the microscope, and then we do some multi-conjugate AO where we use multiple deformed mirrors for correcting the wavefront errors. Sorry, it doesn't work. But as you can see, with this method, now we can achieve a pretty large field of view wavefront control for the spatial varying aberrations, and we apply that to the pathology cases where we try to diagnose the accurate kidney diseases. And if we don't have AO system, as you can see on the below, the membranes in the kidney were totally destroyed. So we can not distinguish the good and the patients. But now with AO, we can clearly see the wrinkles in the kidney membranes, And then that can help us doing the diagnosis for the kidney diseases. Okay. Let me conclude my message. So here, like when people talk about computational imaging, I think what we think in our mind is mainly physical modeling, AI or something. But here I want to show you control. And even the simplest control theory is also very helpful. And I want to thank my collaborator students and like to take any questions. Thanks.
All right. Thank you, He, for the excellent keynotes. Not keynotes, the invited talk. And any question from the audience? At the center.
Great talk. Going back to the sort of control theory approach to the problem, do you need to be in a regime where you have sort of done most of the correction already, and it's sort of fine aberrations that you can linearize, or if I started from really strong aberrations, can I
that's a really good point. Yes, we have to be in some linear region because as I mentioned, for the space telescope, we don't have atmosphere. So the errors is only like a tenth of nanometers large. And for the microscope case, typically we do one round of phase diversities to correct the large errors. And then we do a maintenance for long-term exposure.
And then for the optimal probes, diversity patterns,
yes.
Do you need to know the distribution of the aberration beforehand, or is there something that's optimal for everything?
That's basically optimal for most cases. I can tell you what it looks like. So first, it cannot be very large or very small, because if it's very small, there are no perturbations we can observe. If it's pretty large, then DM has some errors we cannot control. And for the shapes, typically we just have some sinusoidal or sync patterns, which will create very homogeneous illumination. That's probably the best. Yeah.
Any other questions? If not, let's thanks He again. All right, our next speaker is Lahav, and he's going to talk about telemetry as a sensor.
Hi everyone, my name is Lahav, and today I'll present our work with Yoav that sits over here, and Aviad, somewhere here also, and Jason. Telemetry is a sensor, opportunistic wavefront estimation for the James Webb Space Telescope. So we ask the following question: can engineering telemetry already recorded by James Webb inform its optical state? So here you can see James Webb captures dying star in fine detail. So as you can see, it's really an extraordinary science observation, but maintaining this quality image, extremely precious optical alignment. Take a look for a sec. Yeah. Okay. So a little bit about James Webb Space Telescope. As you can see, is enormous. Okay. The observatory itself, it's comparable to the size of a tennis court and roughly as tall as a 3-story building. So it's huge. Now, let's take a look where the telescope is actually located. Okay. It operates about 1.5 million kilometers away from Earth. This is Earth. The sun is down. And from this location, I'm not getting into the orbit so much, but the sun, the Earth, and the moon remain roughly in the same configuration all the time. And together with it, with several other scientific missions, we can see the James Webb on the top. Nice. Okay, so let's get to the core of the problem. What is optical path difference? Please look at the left side. The telescope has 18 independent segments. Okay, they are designed to behave as a single perfectly aligned mirror. And now let's take a look at the side view on the right side. A major deformation is called piston. A piston corresponds for mirror segment that's moving slightly forward or backward along the optical axis. Importantly, we're looking at the relative piston matter. Okay, there is a global piston that, like, all the segments are moving. But it has a small effect, so I won't talk about it. And of course, there are some higher order distortions that also exist that I won't talk right now. So the optical path difference is the deviation between the actual wavefront and the ideal one. Okay? You can look at the effect on the focus. There is the perfect alignment, and the optical path difference changes. So why does it matter? Okay, maybe it's some nanometers, and we don't care at all. So we have a calibration in August, and we have another one in September. And between those calibration, this is the optical path difference. Okay, we can see the mirror slowly drifts. The small drift, okay, it's only 9 nanometer. Although the drift is very small, it accumulates and eventually affects the telescope imaging performance. So this is the misalignment drift. This is without a correction. Can you see the planet over here? I guess you're not. I'm not. So this is with drift-corrected image. Okay, you can see the planet. So small displacements or distortions of the segments affect its output wavefront, and you can see the result over here. Okay, so what we're doing right now. The calibration now, there are many ways to do a calibration, but we're talking about a pointed calibration star. It requires dedicated observation, of course, consumes telescope time, and it's very accurate. What we want to use is telemetry, okay? The engineering telemetry is always available, no observational cost, and continuously collected all the time to know the situation of the telescope, of course, by the ground station. Let's see now a month, okay? We have the measured optical path differences. Those are the drifts. And please look that each time that we have a drift, we can see a mirror correction after that. So when it exceeds roughly 80 nanometers, the telescope performs a mirror correction and brings it back to its nominal range. Here you can see it closer. And let's go back to our question. Can telemetry estimate this drift? So why is it so difficult? Okay, there are two main reasons. The first one, there are hundreds of thousands of pixels per wavefront map. Okay, we have 18 segments, so 30,000 pixels per segment. And over 6 months, we have only 108 data instances for training and testing. So let's take a look of the method overview. First, we have the James Webb. We begin with the engineering telemetry, including temperature, pointing-related signals that we'll talk about. Then we extract the statistics of the signals over multiple time windows, leading to features. And then we use this regression, gradient boosting regression, and PSA coefficient that I'll talk right now. And finally, we reconstruct the optical path difference map. So principal component analysis. As we said, in order to predict tens of thousands of pixels per segment directly is impossible with such a little data. Fortunately, the OPD has strong spatial structure. So therefore, we apply the principal component analysis. First, we take the training OPD map, then we flatten it, okay? And we identify the dominant deformation patterns into 3 values, okay? So instead of predicting every pixel independently, we take these coefficients. So for each mirror segment, there are 2 OPD components that we're talking about. The first one, the relative pistons that we have talked about. And the second one, it's the principal component analysis coefficients that describe the higher order deformation. So all of them are enough for inferent optical path difference. Okay. Let's go back to the telemetry sources that we are using, okay? Here's our James Webb. Please look at the second one, the eSIM, Integrated Science Instrument Model that detects and records the observation. There is the sun shield that protects the telescope from the solar radiation, and the spacecraft bus for communication, power, all the subsystems, okay? So we use this telemetry that was never originally designed for wavefront sensing, from the near-infrared camera that's over there, the near-infrared spectrograph, and the mid-infrared instrument. We use the temperature of 3 of them. Of course, we're using the sun angle and thermal loading. The telescope orientation matters. Here's some PowerPoint animation. Moves a little bit. Since different sun angles create different thermal loads across the observatory. So Now we transform the raw telemetry into features. For each sensor, we compute statistics over 3 hours and 24 hours, okay? We also use, those are the statistics that we are used, and we also use the relative pistons from prior calibration sessions, okay? So we take both of them, and finally, together we have the model input. It's 47 features, 17 from the relative pistons, because we have total 18, and the rest comes from the features from the telemetry. Okay, to learn how to map the telemetry to OPD, we're using gradient boosting regression for two main advantages. The first one, the model is suitable for small tabular datasets, okay? And the second one, it captures nonlinear relationships while remaining easy to understand, and I'll explain later why we need it. So first we have the features. We take an initial estimation at the first tree, okay? Then we calculate what's left to explain the residual, and we do another correction with another tree, and so on, so on, so on, until we have the summarize of all the trees, and this is the final inference, okay? So this is an example of the tree, okay? You can see a decision tree learned by the model. Each node asks a simple question about the telemetry or prior piston values. The final if predicts the principal component analysis, as you can see after the orange thing, coefficient for a mirror segment. So the decision tree rely on a thresholds. What will happen if, okay, look here, we choose feature represent the standard deviation of a telemetry signal over there, and if its value below the 0.01 Kelvin, the model follows one branch. But otherwise, if we add an epsilon, okay, so we'll jump for the other branch. So how robust this model? Can small changes in telemetry abrupt the optical path difference changes? So we tested it also, okay? We perturbed the telemetry around the learned threshold that I won't get it into here, but you can come to my poster and ask some questions regarding it. And we found the threshold crossing produced only minor optical path difference changes. And overall, the model behaved very well under the small perturbations. So this is the histogram with the delta OPD special RMS. And 95% of the perturbations were smaller than 6.4 nanometer. Okay, so let's return to our original question. Can telemetry reconstruct the wavefront change? This is an example from the test set of the wavefront reconstruction. Here, this is the true optical path difference. See the special RMS. This is the estimated one, and the estimation error between them. Looks good, I think. So, explanation criterion. So, to quantify our performance, finally, we use the following criterion. It measures how much the true optical path difference is explained by our model, where higher values indicates better reconstruction, okay? The map on the right shows the results of all the mirror segments. We can see that 13 out of 18 segments with an average reconstruction error of about 12 nanometer is performed here. And the remaining 5 segments are weakly statistical significant, indicating that the available telemetry that we are using may contain less information about the optical state, maybe. Overall, these results suggest that engineering telemetry contain meaningful information about the telescope optical state. Okay, so I generated this. Most of the operation is automatic today, but think how many people and systems are involved in every James Webb observation, okay? As I saw at the beginning of the presentation, just when we see a big drift with 80 nanometer and on, so we're doing the mirror correction 3 days after. So this is why the gradient boosting regression can use as a surrogate decision tree, which is great for us. We can extract some human-readable decision rules, okay? And in the future, such rules may help support calibration scheduling because we can maximize it. Yeah, we don't just have a case that we want to take a picture of something and we have to wait like 3 days. Maybe some nanometers will be okay for my examination and test, and I can maximize where I put it, okay, and scheduling the test. So, in conclusion, engineering telemetry contains information about optical state. It can be integrated into existing calibration workflows, and continuous wavefront monitoring may become possible. So, some future direction. Expand the dataset, of course. Okay, we're doing it on 6 months. We want to expand it. Additional telemetry. We take like the main temperature from the eSIM, but we can take a lot more. Operational integration. We want to see supporting real-time calibration decisions. Okay, and continuous monitoring. That's it. Thank you so much.
All right. Yeah, over there.
Thanks. Very interesting idea. One question I had was, typically these telescopes, like you mentioned, are used for identifying locations of exoplanets and things like that, right? How do we know that the telemetry data is sufficiently reliable to get information that seems relevant? Like, what if you're hallucinating one of the exoplanets or missing them out accidentally?
It's a great question. Actually, before satellite, telescope, spacecraft, whatever is launched, you know, there is a spec that everybody's going over the spec and know the approximation of the values. So if it goes in the same, so we assume that the values are good and we're using it. Yeah.
Here, I have a question on your telemetry data and how much is temperature is the only parameter correlated to the telemetry or the optical path difference? What about the other parameters like mechanical drifts of your actuation?
So it really depends, okay? As I showed, there are some instruments that's used in the eSIM, and each of them, like, there is its own value when it operates or not operate. Even if the orientation of the sun is, of the James Webb through the sun is a little bit different, so the values are different, so it depends.
So is temperature the only, and sun pointing is the only telemetry data that you use, or are there others too?
No, for now we use only the telemetry of the temperatures and the sun, but there are a lot of them. Like, I'm playing with it all the time and it's great. I want to use more telemetry in the future.
Thank you.
Right, our final question.
Hi, thank you for the talk. It's very interesting.
Well, yeah, I don't see you.
Oh, sorry.
Okay. You're standing, so yeah.
But I just wanted to ask some of the mirror segments you had mentioned for the explainability or explanation metrics. Some of them were it was like statistically significant, and some of them were like just weakly statistically significant. Do you have some intuition as to like why some of them?
Well, I don't hear you.
Sorry.
The last sentence?
For those like mirror segments and then explanation metric slide that you had put, and some of them were statistically significant, some of them were just weakly statistically significant. So then I was just wondering, do you have some intuition as to why some of them?
Okay, actually this is the most interesting thing, I think. This is the next stage for me, to see inside the 18 segments. On the left, there are more like less significant than the right. So it's interesting, and for sure I want to explore into the future. Yeah.
Yeah, let's thank Lahav.
Thank you so much.
Yeah, our next talk we're gonna be towards blind lens aberration correction via a large lens library pre-training and discrete degradation priors.
Good morning, everyone. I'm Dejun Ling. Today, I'll give a talk representing the first author of this work and my colleague from Zhejiang University, Xiaolong Qian. And thanks for the introduction. And please allow me to read the script because I want to express the exact same as the author is intended. The work is about the blind lens aberration correction via the large lens library pre-training and the discrete degradation priors. The goal of this work is to build a scalable blind aberration correction framework. In particular, we want to model the correct diverse unknown lens duration without requiring the target lens point square function calibration at the inference time. So the residual lens aberration are common across optical systems. They can come from optical design trade-offs such as the size, the field of view, and the aperture. They can also become more significant in the simplified optical systems such as the single lens systems and the meta-lens systems. In addition, even complex lenses may suffer from the manufacturing or the assembling errors. And these factors lead to the different types of the lens degradations that vary across the images. In other words, the degradation is not uniform, but changes the field view. And this makes aberration correction a very important challenge in the computational photography. A conventional solution is non-blind aberration corrections, and where we firstly calibrate the point square functions of the target lenses, and then train and apply a lens-specific correction models. This can be effective, but it's hard to scale. The accurate point square functions are very expensive to obtain, and they depend on the lens design, the field positions, the wavelengths, the focal, and the assembling conditions. So the blind aberration correction is more practical settings. The model only takes the degraded images as input and does not require the target points functions at the inference times. The key question is, can we still benefit from the point square function-based physical guidance while keeping the pipeline blind? The recent lens live pre-training pipelines provide a very promising directions. They train a universal blind correction model using a synthetic lens libraries, as we show in the figures. And however, there are still two bottlenecks. The first one is the data foundations. Existing lens libs can have bias degradation distributions and limited scalability when simplified decreasing the data size. The second bottleneck is the model diagrams. The most methods use a one-pass restoration networks without the explicit point square function-based physical guidance. So we need two things. The first one is the scalable and the balanced lens lab, and also a blind mechanisms to retrieve the point square function-based degradation priors. So to address the two bottlenecks, we propose the FONT-CAC, that is the foundation model for the computational aberration correction. The FONT-CAC consists of the two key components. The first one is the AOD Lab Pro, that is the automatic optical design library pro, which improves the data foundations by constructing a more balanced and scalable lens lab. Which is improve the data foundations by constructing a more balanced and scalable lens lab. The second is the latent point square functions representations. We can call it LPR, which has introduced the point square function-based physical guidance into a blind correction pipelines. So in short, the AOD Lab Pro addresses the data bottleneck, while the LPR addresses the missing prior bottleneck. And let me first introduce the data foundations, AOD Lab Pro. The existing lens labs are typically generated by the automatic optical design, which make it possible to synthesize a large number of the lens systems. However, the sampling is often driven by the lens design parameters or the RM-based optical design parameters. So as a result, the final image-to-domain degradation distribution can still be biased. So to address these issues, the AOD Lab Pro samples lens is based on the image-to-domain degradations. We firstly expand the lens source with more diverse optical specifications, including we can add the aspheric lens surfaces and also the image-to-plane perturbations. So for each lenses, we render simulated checkerboard patterns at the key field view and measure the resulting image domain degradations. And based on these measurements, we classify each lenses by the two factors, the degradation, severity, and the spatial variation trend. And this gives us a very hybrid sampling bias. by balancing both severity and spatial variations, the AOD Lab Pro provides a broader degradation coverage for the lens lab pre-training. And next, we introduce the model foundations, the latent, the point square function representations. The training consists of the 3 stages. As we can see on the left, this is the stage 1. We firstly use the ground truth point square functions to build a discrete PSF prior space. The PSpace encoder extracts the PSF features, and then the VQ codebook turns them into a discrete degradation priors. In the second stage, in the middle, the pipeline becomes blind. Given only the degraded images, a predictor retrieves the corresponding degraded LPR from the learned codebook. And in the stage 3, the target-specific adaptations, we freeze the codebook and fine-tune the predictor and restoration networks. This helps to regularize the adaptation, especially when the target is limited. So the key point is the PSF guided during training and fully blind at inference. And to understand whether the LPR learns a meaningful priors, we visualize the latent space using TSNE and different lenses from the separate clusters, showing that the LPR captures the lens-specific degradation patterns. And more importantly, the predicted LPR stay close to the corresponding ground truth, the point square function priors. This indicates that the blind predictor is not learning the arbitrary images features. Instead, it is retrieve the lens-aware degradation priors from the learned LPR space. And here we show the zero-shot correction result on the real captured lens degradations. And this covers the different optical systems, including the single lens systems that we show, the 2 simple lenses on the first and the second row, and also the meta lenses we show on the 4th row. And we also show the several high-end lenses from Canon and Sony. The font CAC restore the sharper structures and reduce the color artifacts compared with the previous method. This is important because the model is trained on the synthetic lens lab data, but it can generate to real aberrate images. And we further evaluate the zero-shot performance quantitatively. In the upper tables, replacing our old model, and here our AOD Lab Pro improved the average PSNR from 25.14 to 25.91 dBs. And this shows that the AOD Lab Pro provides a broader degradation coverage. And on the top of the AOD Lab Pro, the font CAC further improves the average of the PSNR to 26 dBs and showing the benefit of the LPR-based prior guidance. The lower table shows, on the left, shows the LPR is also effective across different backbones. It improves the NavNet, the swing IR, the UNet by 0.21, 0.41, and 0.66 dBs respectively. So both data foundations and the LPR model designs contribute to the zero-shot generalizations. And based on the single-shot generalizations, the font CAC can also enable efficient target adaptations. For the specific unseen lens, we freeze the LPR codebook and fine-tune the rest of the networks. This constrains the adaptation within the learned optical prior space and helps to prevent overfitting. The improvement is especially clear in the few shot settings. For example, so on the single lens 1, the field shot adaptation improved from the 21 dBs and with a scratch training to 30 dBs with the font CAC pre-trainings. And this shows that the LPR is useful not only for the blind generations, but also for the data efficient adaptations. So a very brief conclusions. This work represents the font CAC for the blind lens aberration corrections. And first, the AOD Lab Pro includes a scalable and balanced lens light. And secondly, the LPR enables the blind retrieval of the point square function-based degradation priors. And thirdly, the font CAC achieved the strong zero-shot generalization and efficient field shot adaptations. And overall, the font CAC make a blind aberration correction model more scalable, physically grounded and acceptable. And if you're interested about the model and the work, please feel free to have a glance at the paper, visit the website, and if you have any questions, feel free to ask questions to the author. And here's the email. Thanks.
Yeah, great. I think for this paper, we're gonna skip the Q&A session because the authors couldn't attend in person. So let's directly move to the next talk. In next talk, we're gonna be learnable coded aperture for real-time imaging through turbulence.
Good morning, everyone. My name is Li Hanshi, and presenting on behalf of Jiang Dongyu and his co-authors from USTC and Tsinghua University. And due to the visa issues, none of the authors could attend in person today, and they welcome any questions via email after this session. And the title is Learnable Coded Aperture for Real-Time Imaging Through Turbulence. Atmospheric turbulence arises from random refractive index fluctuations along the optical path. These fluctuations distort the PSF, causing blur, detail loss, and structure distortion. And this is a central challenge wherever light travels extended distance, surveillance, and astronomy, and remote sensing. A practical system demands three things simultaneously: high restoration quality, real-time speed, and easy hardware integration. And two main categories address this problem. First, adaptive optics. And this system directly compensates wavefront distortion at the optical front end. They are effective, but hardware complex and costly to deploy. And second, computational restoration. Purely algorithmic, easy to deploy, no hardware modification required, but it can only recover information that survives the degraded measurement. And once the imaging process discards frequency content, there is a fundamental information bottleneck. A multi-frame method extended computational restoration by exploiting temporal redundancy across frames. They often achieve superior quality, but registration overhead and computational costs make them unsuitable for dynamic scenes and real-time deployment. And so here's the question. Rather than passively inverting degraded observation, can we make the measurement itself easier to restore? And our answer is coded aperture. And turbulence is a natural target for pupil plane coding. And the key insight is that turbulence perturbs the phase of the generalized pupil function, while a coded aperture manipulates at the same physical layer. The coding acts exactly where the degradation originates. And by breaking the circular symmetry, the coded aperture reshapes the PSF and MTF, redistributing frequency response to retain more useful information in the captured measurement. And this makes the inverse problem fundamentally easier for back-end network. And the physical imaging model is differentiable. So image domain losses backpropagate directly to the aperture parameters. The pipeline takes a turbulence phase screen, combines it with the learnable aperture to form the generalized pupil function, derives the PSF through Fourier optics, and produces the degraded observation via convolution and noise injection. And this enables end-to-end joint optimization of aperture and network. So for real-time restoration, we designed Chromium. The design motivation follows directly from turbulence physics. Degradation appears locally as blur, but originates from global optical transfer changes caused by full aperture wavefront perturbation. We need both local detail recovery and long-range modeling at real-time speed. And Chromium uses a multi-scale U-shaped encoder-decoder. The core is a hybrid conv member block containing a convolutional branch for local high-frequency extraction and a member branch for global dependencies with linear complexity. And outputs are fused through a residue connection. And here is a critical subtlety in code design. when we jointly optimized a strong backbone with the aperture from scratch, the network absorbs most of the inversion burden, weakening effective gradients to the aperture. And the aperture gets stuck in a local optimum near a circular aperture. And our solution is two-stage strategy. In stage 1, we pair the aperture with a deliberately weak backbone. The network cannot fully compensate, so optimization pressure falls on the front end, forcing the aperture to discover generally useful structure. And in stage 2, we freeze this discovered aperture and transfer it to strong backbone. We train the strong backbone first to build stable representations, then optionally fine-tune both jointly. This ensures the strong backbone exploits the coding gain rather than overwriting it. And here is the system performance. And Comia Plus coded aperture achieves the best performance across all 3 turbulence levels, surpassing all purely algorithmic methods. The average gain is plus 1.22 decibel PSNR and plus 0.026 SSIM. And critically, it remains real-time at 45 frames per second, delivering superior quality. And looking at the enlarged patches, and Comia with coded aperture restores sharper edges, clearer textures, and more faithful structures, especially on the medium and strong turbulence where information loss is severe. And a natural question is, does the gain require task-driven optimization or just a non-circular shape? And we compared against a triangular, star, mural, and manifold design aperture, and all fixed. Most actually degrade performance. And they reduced transmittance, lowering signal-noise ratio with directional bias misaligned to the restoration objective. Only the jointly optimized aperture consistently outperforms circular across all turbulence levels while maintaining 89% transmittance. And this gain comes from optimization and not shape change alone. And this table validates the two-stage design, directly joint optimization with the strong backbone yield only plus 0.14 decibel. Our two-stage strategy achieves plus 1.22 decibel. The discovered aperture also gives turbulence a plus 0.38 decibel, confirming the improvement originates from the front-end observation. Generalization is critical for practical deployment, and here all models are trained only on the strong turbulence and evaluated on weak and medium, which constitute a strict distribution shift. And purely algorithmic methods tend to overfit when model capacity is increased. After introducing the coded aperture, even when the task distribution deviates from training, the gain remains significant. And the coded aperture reshapes observation statics at capture time, reducing the network's dependence on training distribution. And what does the optimized aperture do optically? In the spatial domain, it exhibits a dual ring transmittance structure, a high transmittance central region paired with an outer edge ring. And this narrows the PSF main lobe, improving resolution. In the frequency domain, the MTF difference map shows enhanced low to mid frequencies while suppressing the outermost high frequency band. And this trade-off aligns with single frame restoration. Low and mid frequencies carry structures and edges, while the highest frequencies are most fragile under turbulence and hardest to recover from a single frame. Let me summarize the contributions. First, we proposed a learnable coded aperture that reshapes PSF and MTF, making turbulence degradation easier to invert. Second, we designed Comia with 5.25 million parameters, achieving 45 frames per second real-time restoration. Third, we introduce a two-stage strategy that decouples aperture discovery from back-end training. Fourth, we provide systematic validation showing theta across all turbulence level, back-end independence, and strong generalization. Looking forward, we plan to extend this framework to spatially varying and multi-frame settings. Most importantly, we aim to fabricate the optimized aperture and validate the entire system on real optical system. And thank you for your attention. The authors deeply appreciate for your understanding regarding this issue. Since none of them could be here today, if any experts or professors have questions, feedbacks, or collaborations, please reach out to Jiang Dongyu via email showing on the screen, and they will respond as soon as possible. And thank you very much.
Thank you, Lihan, for presenting the paper. Let's skip the Q&A as mentioned. So we're going to have our last paper to be presented. So the Hadar, we're going to present this towards extended field of view wavefront shaping, a benchmark of structural priors and phase accuracy. All right, so let's welcome Hadar.
So hello everyone, I'm Hadar Cohen, and this talk is an attempt to think on how to do wavefront shaping over a large field of view. To explain the problem, consider a simple microscopic setup where we use a 4F relay to image the light emerging from a tissue sample. When light emerges from a point at the front of the tissue, we can focus the microscope and see this nice sharp spot on the detector. But when the source point is located deep inside the tissue, the light scatters on its way to the camera, and instead of a sharp spot, we see this heavily abraded image. To overcome the distortion, wavefront shaping systems use an SLM. The SLM attempts to correct the aberration, so now the light is focused into a single spot on the detector, like in the case of the thin tissue. However, the biggest problem with wavefront shaping correction is that they only apply for a very small field of view. While the light emerging from the central point, as you can see here, is corrected, if we look at a light emerging from a nearby point, it travels through different cells inside the tissue and therefore undergoes a completely different aberration. So we simply cannot correct it with the same SLM modulation. To image a large area, you therefore need multiple wavefront shaping corrections. However, estimating each correction is a time-consuming process. So ideally, we want to measure corrections at a sparse set of points, and from them predict the corrections everywhere else. And the main question of my research is, how do we do this interpolation? To describe the problem mathematically, we use the transmission matrix, or TM for short. Think of a TM as a huge matrix that describes how every point inside a tissue looks after scattering. For example, let's take source point E1. After passing through the tissue, it generates a wavefront called T1, and this is the first column of our transmission matrix. Then E2 gives us T2, E3 gives us T3, and so on. And if we know these vectors, we know what corrections to place on the SLM, because the correction is simply the inverse of the distortion. But in practice, each time we run wavefront shaping correction, we measure only one column of this matrix. So our goal is simple. We measure a sparse set of columns and reconstruct the rest through some sort of smart interpolation. This research compares several different approaches to this transmission matrix interpolation, which I'll explain in the following slides. The first approach we consider uses the memory effect property. This is a well-studied property of speckles. It states that speckle patterns from nearby points are simply shifted, correlated versions of each other. For example, here we can see 3 speckle patterns from 3 fairly close points, and we can see that there's a shift correlation between them. This property states that we can predict missing transmission matrix column from nearby measured column. However, the memory effect correlations only hold when the points are very close to each other. So in practice, it turns out to be the weakest approach in our evaluation. Still, this is a baseline used by most existing wavefront shaping systems today. We saw that tilt-shift takes a column from the transmission matrix and uses it to predict other columns. But this does not account for the physical source that generated these columns, namely the 3-dimensional structure of the tissue. Since all of these aberrations result from the 3D structure of the tissue, we thought that instead of just interpolating directly between them, it would be more principled to first reconstruct the three-dimensional tissue structure. And from this structure, we can analytically compute any other missing column. For the 3D reconstruction, we modeled the tissue using the multi-slice model. In this model, the tissue is described as a collection of thin phase layers, row 1, row 2, row 3, etc., between which light propagates in free space. We used the multi-slice model to suggest another way to interpolate the missing transmission matrix column through diffraction tomography. The idea is to run gradient descent optimization, searching for the 3D layers that generate the sparse set of transmission matrix column we measured. Once we find them, we can simulate any missing column. The advantage of this approach is that it uses a physically accurate model of the aberration, but it's also computationally heavy, sensitive to noise, and prone to getting stuck in local minima. The next approach also recovers the 3D structure, but uses a linear approximation to do so, which is valid when the aberration is weak. Since the problem is now linear, it solves much faster and does not get stuck in local minima. The cost is, of course, the reduced accuracy. As before, once we've estimated all the volume layers, we can simulate any missing column. So up to now, we've been discussing mostly physics-based models. The second direction we explore is moving to data-driven models. And the motivation is simple. Physics-based models like diffraction tomography, they involve heavy computation, and they are also sensitive to noise. So the idea was to explore learning-based methods, hoping that they will be faster and more robust. For that, we need the training data. I want to add a disclaimer here. All the training data that you're going to see in this work is synthetic, meaning we're working with simulated tissue. And specifically, we use a synthetic volume containing random spheres, as you can see here. The random sphere is meant to mimic the distribution of cells within a real 3D tissue volume, and this gives us a simple model that approximates real tissue to some degree. Most importantly here, our goal is not yet to produce a clinical solution, but to explore a concept and understand the problem. Given the synthetic training data, we can explore learning approaches for transmission matrix reconstruction. The first network we explored is called the TMAT-net. It takes as input TMAT transmission matrix columns and learns how to interpolate the missing ones. The network simply learns to reconstruct the columns without modeling the 3D structure. In contrast, we designed another network called VolRefNet that explicitly accounts for the 3D structure of the tissue. It takes the column we measured. First, it tries to reconstruct the 3D volume. From that volume, it then predicts the missing columns. There is thus a physical constraint here, namely reconstructing the volume, and we will see that this constraint is very significant. All right, so let's summarize the 5 methods we compared in this work, starting from the simplest approach, tilt-shift memory effect, which assumes a planar aberration. We progress gradually to 3D models, physics-based methods like diffraction tomography, and methods that assume linear approximation, like the weakly scattering firstborn approximation. Then we saw 2 data-driven methods, TMAT-net, which performs direct interpolation from the data, and VolRefNet, which is more complex and requires the network to also succeed at 3D tissue modeling. The central question of this work is which approach gives the best results, of course, under which conditions, and what combination of physics and learning actually works for us. Using our training and test data sets, we evaluate all methods under the same condition, and I will skip the technical details due to the time constraints. But in essence, for each approach, we simulated what would happen if we placed the inferred wavefront shaping correction on top of the SLM and measure how much light reached the desired sensor point. This table shows the numerical results according to our wavefront shaping quality matrix. We examined 4 cases with different amount of scattering, different amount of ODs, which means optical densities, and different densities of the measured columns. As you can see, 1%, 1.5. The rows are sorted from the worst performance at the top to the best performance at the bottom. And the clearest finding is that every 3D method significantly outperforms the tilt-shift memory effect. This is a very important observation, given that tilt-shift model is a common practice in many wavefront shaping systems. Diffraction tomography gives the best results in every condition. Volref approaches it, particularly when the sampling density is low. TMATNet, however, shows almost no improvement whatsoever over the linear weakly scattering approximation. And the conclusion is that using a neural network, training a network by itself is not enough. The physical constraint is what makes the difference. Apart from focusing quality, we can take a look at what the reconstructed 3D structure from the different methods actually look like. And we start with the supervision signal. Shown in two forms, we have XZ cross-section that you can see here, and two XY cross-section at different depths. Now let's look at the results. Diffraction tomography does not reconstruct well, especially at the shallow depths close to the point sources. You can see Z equal 5. This happens mainly because there are regions that were simply never measured. Each column we measure is a wavefront that emerges from a single point. And since the microscope has a finite NA, we only measure this wavefront within a finite column. If we measure only a sparse set of columns, there are areas of the volume between the measured points that were not included in any of the cones. So therefore, the measurements do not provide enough information to reconstruct in these areas. The linear weakly scattering is even weaker than diffraction tomography, which is not surprisingly and roughly as expected from such a simple model. The interesting observation is that VolRefNet produces volumes that look much smoother and nicer and are visually close to what the network saw during training, its supervision signal. But here comes something interesting. Diffraction tomography, despite looking worse, achieves better optical focusing results than VolRefNet. This highlights an important observation. The fact that something looks good visually does not necessarily mean it's physically correct, especially when talking about optical phase. In wavefront shaping, what matters is the accuracy of the phase far more than how the volume looks to the eye. What we see in VolRef may be some kind of hallucination. The result looks smoother and nicer, but in practice, it does not accurately reconstruct the transmission matrix. Therefore, its performance is worse, especially in the challenging cases where phase accuracy is needed and crucial. So before concluding the talk, let's summarize the main things we learned from our evaluation. The first conclusion is that 3D modeling is critical. Every method that genuinely accounts for three-dimensional structure of the tissue achieves a significant improvement in results compared to the tilt-shift memory effect. The second conclusion is that physics-informed learning works better than free learning, meaning learning that is not guided by the physics of the problem at all. We saw this directly in the comparison between TMATNet and VolRefNet, which incorporates the volumetric prior. As I mentioned before, our problem is not just about reconstructing a volume that looks good, a structure that looks good. The real objective here was to reconstruct the optical phase very accurately. Here, a key point emerges. There are probably no free lunches. Networks like UNet and neural networks in general, they have this inherent bias toward producing smoother, more regular signals, similar to what we see in natural images. But in our case, the signal we are trying to reconstruct is much more pseudo-random and much less smooth. So the network struggles to reconstruct it accurately. The research conclusion is that the future direction should combine physical models with deep learning, incorporating both structural priors and physical constraint on the phase. In summary, we evaluate a range of transmission column reconstruction techniques and obtain a roadmap that shows not only what works better, but also the limitations of current approaches, where they lie, and how to think forward to go beyond them. Thank you very much for your attention. Are there any questions?
Any question? Please raise your hands or come to the microphones. Yeah, over there.
Hi, thank you for the talk. It's very interesting. I just wanted to ask about that future work slide or future work direction that you mentioned. So would that be having that VolRefNet, adding some data consistency terms or just iteratively doing some data consistency regularization loop? Or?
So exactly. This is exactly what we're going to do. And we also need to take it into the real lab and start getting and start acquiring real tissue data, which is a difficult task, but this is what we're going to do next. So,
Thank you.
Right there.
Yeah, very interesting conclusions. I mean, it's surprising that like the diffraction tomography performs best, like, and better than the neural networks. So my like the following up question would be that, like you said that the UNet itself has spectral bias. It will favor the low frequency components. What like the I mean, have you considered like the trying like the different neural networks? I mean, recently there are some neural networks or like architectures that do not have like the other claims that they can beat the spectral bias. I mean, maybe this kind of neural networks can prove that data-driven like the approach can work. Again, I mean, you currently like the diffraction tomography. I mean, it's multi-slice model. It's based on physics. I mean, yeah, surely it does not have spectral bias. Maybe if you try like the neural network with different architectures, that might have changes.
okay.
Yeah, what do you think?
All right, so this is a very good question. And yes, we tried various ranges of neural networks, not just the UNet and basics. But there's still much more work to do, and your question is touching exactly what we're planning to do next. So thank you.